All right, everybody, so this is the video for the Matlab version of Lab 5, the forward and inverse kinematics of a two-link robot arm. So first off, I'm going to review how matrices and matrix math works in Matlab. If you already know that, you can go ahead and fast forward. You also should have already watched part of the Matlab refresher I posted last week for last time for Lab 4. Go ahead and scroll through that. If you have any questions with those, let me know. For now, I'm just going to go ahead and continue. So I can create a 2D array using the square brackets. I use commas or spaces or both between my values in the same row. Then to make the next row, I put a semicolon and continue on. And Matlab doesn't really care about the indentation or the white space. So if you'd like, you can always put these on the next row to remind yourself that it's a 2D array. And if I take off that end semicolon, it'll show up here in the command window. 1, 2, 3, 4. Awesome. You can also do some math with arrays. I can add to every index in X by saying X plus 2. There's every 1, 2, 3, 4 plus 2 each. I can subtract, same thing. I can multiply, but only if the multiplier is an integer. Is a single value. It's not in an array. I can multiply it by a float too if I wanted. Stuff like that. Because this is a single value. If I wanted to multiply by a 1 by 2 array, let's say I wanted the first column to be multiplied by 1s and the second column to be multiplied by 2s. This isn't going to work because a 2 by 2 array cannot be multiplied by a 1 by 2 array. It's going to freak out. So in that case, I'd want to do a dot times, which means element-wise multiplication. And if I unpress that, first row was multiplied by 1, first column was multiplied by 1, second column was multiplied by 2. If I wanted to do full matrix math, which is the dot product of an array, I'd have to make sure that the sizes are compatible. So 2 by 2 multiplied by 2 by 1 is allowable. We took the first row, multiplied each element by the first column, and then added them together. 1 times 1 plus, let's do this so we can remember that it's two-dimensional. Okay, we did 1 times 1 plus 2 times 2, 5. 3 times 1 plus 4 times 2, 11. So that's what that looks like. If we had a 2 by 2 array, you can do that. By the way, Y is currently what's called the transpose of X, which means every column became a row and every row became a column. Stuff like that. So basically just flips the whole array around this center line. And there's that. Also, matrix multiplication, the order of operations is very important. X times Y is not the same as Y times X. So just keep that in mind. When you're doing your transformation matrices, make sure that they're in the right order as we talked about in lecture. You can also build arrays. So you'll want to be building your arrays of rotation matrices and your translation vectors into a transformation matrix. And that's gone over in the lectures as well. But here's just an example of building a matrix. If I want the first, let's do this. I can treat each of these as single objects. So if I want the first row to be X next to Y, I can say X, Y. and they're put together in the same row. And it smashed them together because they were of compatible sizes. If I wanted to add an extra row to that, as long as it was the same width as the first row, I can bundle those all together, just like that. And that's what you'll use to build your transformation matrix. Cool. Some other things, you can also return a matrix as part of your function. So if we wanted to do, let's see, in some functions, you can't return, in some programs, you can't return a matrix because it doesn't like complex data structures. But in this language, we can. So if I wanted to just build an array all made out of x's, I can. So that's how you build a function. We went over that in the last one. But the thing is, when you have a function, let's do this. It needs to have the same name. So there we go. We saved that. And if I wanted the demo of 2, that's how I return a matrix out of a function. There's also a lot of other cool function things. You can build an array of just ones. So you use the word ones, and then here you would put the size of this array that you want. If you want it to be square, you can give it just one number. If you want it to not be square, you give it 2 numbers. So 2 rows, 3 columns, maybe. There's that. And you can have as many dimensions as you want because this is Matlab, the matrix laboratory, and it loves matrices. So there's that. You can also make an array of zeros. Cool. And then you can make what's called an identity matrix, which means it's zeros except for the diagonal, which is ones. And that is useful because any matrix multiplied by the identity is itself. So if we have y equals 1, 2, 3, 4, 5, 6. Also, this works best when it's a square. So if we have y times x, it just spits out the same value of y. When you're doing your matrix multiplication, multiplying the transformation by a point, it's going to look a little different. So first off, this bottom row will be 0, 0, 1. Cool. And 3 and 6, those are fine as x and y's. But the rotation matrix, there's actually a special hint in here. Because it's always made of cosines and sines, that means that the magnitude of any little column or row here will have to be 1. So 1, 2, 4, 5, that doesn't work. But if we were to say do a rotation of 90 degrees, that's cosine 90 is 0, negative sine 90 is -1, sine 91, cosine 90, 0. Cool. So that's a transformation matrix with a 90-degree rotation and a 3/6 translation. But if we try and multiply that by a point xy, it won't work because the matrix dimensions aren't compatible. So instead, what we have to do here is if we add a 1, it doesn't change the multiplication at all, but it gives us the right dimensions that we can multiply with. And also, made a mistake there. This should be a column vector, which means we have semicolons. So let's try this again. Cool. So the 0.35, after rotating by 90 and translating by 3/6, is -2, 9. And then when you're actually taking the point, you'll ignore this 1 because that was just added for our matrix math. In terms of the tester script, what this gives you, let's do this. This gives you 4 different structs. First one is for the rotational tests. And in the rotational tests, what it has in here is 2 theta values. So it'll want you to find the rotation matrix with the first theta, then it'll multiply it for the rotation matrix with the second theta, and this should be your output rotation matrix. So the reason I did that is so that nothing ends up hard coding. If you multiply 2 different thetas together, it should be doubly sure that your rotation function works. Similar thing for the transformation. It's going to give you, let's do this. So here, let's do this, trans 2D tests dot inputs. Cool. So here's your first theta, first x, first y, second theta, second x, second y. It's going to build 2 transformation matrices, and then it's going to multiply them together for this output is what it's looking for. You shouldn't have to deal with that too much. The test script should handle everything, but if you wanted to know how that was made. And then, let's see here. For the forward kinematics tests, you have 4 inputs and 4 outputs. So if we take a look at the document on Canvas, go. The Canvas document will tell you how the inputs should be listed. There is an order to them. So if we show this, we are looking at the Matlab version. Cool. So the inputs given are the length of the first link, the length of the second link, and then theta 1, theta 2. And if we look at the robot kinematics lecture, we can see that we do the forward kinematics by first building a rotation of just theta 1, and the translation for that would be 0. So that's world to 1. And we can use that with just the rotation matrix and translation of 0. Your second step is the rotation of theta 2 and the translation of L1 in the X. And then the last part is a rotation of 0, which comes out to 1, 0, 0, 1, and a X translation of L2. So you'll build those with the transformation code that you just made. And then when you give it, let's see here, forward kinematics tests 1.inputs. So when you give your function L1, L2, theta 1, theta 2, it should come out with these outputs. And in document, it shows what order that should be in. It should come out with P2 and P2. And this will be P2 X, P2 Y, P2 X, P2 Y. And again, the testing script will handle the comparisons of those. Let's see here. So for instance, this one here, we can see that if our first length is of length 3, that means, and there's no rotations here, that means that the first link ends and the second link begins at position 3, 0. And then we have a link 2, length of 1. And so we just add 1 to that in the x direction. And we can kind of see how that would come out logically. The rest are random. So making sure that your function works correctly. For the inverse kinematics tests, we have 4 inputs and 3 outputs. So let's take a look at the order there. Order of the inputs are L1, L2, X, and Y. So given, let's see here. Link 1 is 2.5, link 2 is 4.5. What would be the joint angles, and is it possible to reach this point, X, Y? And then it would return the 2 thetas, theta 1, theta 2, and this last variable is a Boolean for reachable. You can tell if the point is reachable because the inverse kinematics equations would come out with a complex number, with an imaginary part. So you might want to look into the Matlab function of MathWorks. And if we take a look at complex numbers, cool. We can separate them using real and imag. So if the imag is greater than, if the absolute of the imaginary is greater than 0, that means that the position is not reachable. So you'll have to check for that at each step of your calculations. And then when you write the inverse kinematics function, I would definitely recommend splitting this up into parts. It'll help you go back and solve it by hand if you need to. So the way I did it is I used the a cosine version, and if you split this up into like numerator and denominator or something like that, that can really help. Let's see what else. And then when you get over here, definitely separating it out into psi, alpha, stuff like that will help. Yeah. Or you could do it like this. The A10 works too. We don't care about the elbow up, elbow down solutions. If that's been mentioned in lecture, just go ahead and give the first theta that works. Cool. So it's the inverse kinematics function. And then finally for your drawing script. There we go. So basically for this one, I'm looking for a complex, maybe pretty path. There were some examples posted on Canvas. All you really have to do is create your lists, and then also, let's go to the one that I gave you instead. There we go. Cool. You'll create your lists, make some arrays. So you'll have to have somewhere to store theta 1, theta 2, P2, P2 for every coordinate in your path that you create. Every coordinate will have a different value for those guys. You call your functions with a for loop, and then you'll have to recreate. Here I've plotted for you the x and y versus time. You'll have to recreate for theta 1, theta 2 versus time, and then it will save as a video automatically for you. So yeah, that's the MATLAB description for this lab.